Hey, I'm Luke.
My name is Brett.
My name's Damion.
And we are going to tell you about the Ultrasonic Math Music Robot. While playing the math game, you might find yourself changing your answer. Luckily, our product allows the user to delete an incorrect input by pressing the star key. If the user got their answer correct, they should hear a corresponding higher-pitched beep with a head nod. Otherwise, they will hear a lower-pitched beep with a head shake. The user can exit the game by selecting the pound key. The user will then see a score and accuracy rating for their game. The music game trains the user for pitch recognition. The user will place their hand over the ultrasonic sensor and adjust the distance to change the pitch. The user selects the pitch the same way as the math game, and the robot will also respond accordingly.
The software architecture is pretty simple. There's a main event loop that indefinitely prompts the user with math or music game, and each of the games exist in their own files with their own main loops and functions. So when the user selects one of these games, the program jumps to that respective game's main loop, and it'll remain in that indefinitely until the user selects exit, at which point the score and accuracy will be displayed, and then you'll re-enter the main loop again, and that overarching loop runs while the system has power. One of the most challenging things to implement was converting a distance in centimeters from the sensor to a frequency, and then converting that frequency to a note, all quickly enough while the user is hovering their hand over and distance is being sampled like 5 times a second.
I started out with the speaker. So the speaker right here with the robot actually makes music, or makes the noise. I had to add an operational amplifier to amplify the voltage so the speaker can actually create the audio cues that you heard in the video before. Then some of our components, like the ULCD, the screen right here, actually needed 3.3 volts in order to actually operate correctly. But in order to do that, I had to use the 5-volt converter. Then I used a buck converter to go from 5 volts to 3.3 volts. Then we used that to power up the ULCD. And as I worked on the PCB, the main challenge on the PCB was actually getting the right footprints. The footprints was kind of hard to match the components that we actually used in our robot. So getting it from footprints to actual components and without having any errors whatsoever was really difficult and took a huge learning curve since this was everyone's first time trying it out.
We originally were going to 3D print all the components for our chassis, but opted for laser cutting wood for the sake of strength and time. We designed all the cuts and engravings in Adobe Illustrator and opted to glue all the permanent connections and use screws and washers for all the temporary connections, allowing the robot to be fully disassembled if needed. The biggest challenge for the mechanical system was the pan and tilt mechanism for the head. We had to ensure strong, effective communication with the software subsystem so that the servos would move proportionally to the head size, and we had to ensure the head was not too heavy for the servo specifications. Team 9 out.